Hello students, today we will discuss about the standard delay unit. Okay, in previous videos we have discussed about the seat resistance and standard unit capacitance. Okay, so seat resistance, it is the channel resistance for same length and width ratio of the transistor. Okay, so that is the seat resistance, and standard unit capacitance, minimum feature size of the transistor, and its capacitance, it is 1 square Cg. So now time delay is measured in terms of standard unit tau. It is defined as a product of Rs and Cg. So that is tau is equal to Rs into square Cg. Rs is a seat resistance and 1 square Cg is a capacitance of minimum feature size transistor for given technology. The measurement of tau, consider nmos driven by a pass transistor shown in figure below. So nmos inverter, is driven by a pass transistor, and the length and width or dimensions are indicated here. So length as to width ratio is 1:1. Length as to width ratio is 1:1. So for this inverter, pull-up transistor is having length as to width ratio is 8:1, and pull-down transistor, it has length as to width ratio is 1:1. Pass transistor is having length as to width ratio is 1:1. Okay, pass transistor is on for given gate voltage, that is equal to VGG is equal to 5 volt. Okay, pass transistor will on. Now pass transistor is represented by its seat resistance Rs. So due to equal length and width, it is represented by Rs. Okay, so pull down transistor of inverter is represented by capacitance, that is 1 square Cg capacitance, as its length and width are equal, and hence it will be represented by 1 square Cg. Okay, since pull down transistor has minimum dimensions, as pull down transistors has minimum dimensions, hence it is represented by 1 square Cg. Okay, now tau is defined as time taken by capacitor to charge from 0 to 63.2% of the maximum value as shown in figure. Tau is a time constant required to charge the capacitance from 0 to 0.632 of applied voltage. Okay, or 63.2% of the applied voltage. Okay, so this is the time constant tau and time required to charge the capacitance. Okay, so this is the equivalent circuit of the circuit. So this is the resistance of the pass transistor, and this is the capacitance of the input stage of the inverter. Okay, so therefore time required to charge capacitance, that is 1 square Cg capacitance, through a minimum resistance Rs. Okay, this is about the 1 tau, time required to charge the capacitance from the 0 to 0.632 V or 0.63.2% of the supplied voltage. Okay, so now we will discuss about the inverter delay. So we will discuss about the nmos inverter delay and cmos inverter delay. So in case of nmos inverter, so already we have discussed about the nmos inverter. It will have one pull-up transistor and one pull-down transistor. Let us take one pull-up transistor, that is Z pull-up. It will have length as to width ratio is 4:1, and pull-down transistor, it will have 1:1 length as to width ratio. Now already we have discussed how to calculate the resistance of pull-up transistor and resistance of pull-down transistor. Resistance of pull-up transistor RPU is 4 Rs. Okay, it is 4 times, and that is equal to 40 kilo ohm, and resistance of pull down transistor it is minimum, and that is equal to RS, that is equal to 10 kilo ohm. So already we have discussed how to find out this resistance of pull up transistor and pull down transistor, and we have solved it. And so resistance of 4:1 inverter, 4:1 transistor, it is a 40 kilo ohm, and resistance of 1:1 transistor, it is a 10 kilo ohm. So it is n type transistor. So resistance of n type transistor, it is a 40 kilo ohm for 4:1, and pull down transistor, that is 1:1 n type transistor, it is a 10 kilo ohm. Okay, so delay associated with the inverter depends on and off of condition of the transistors. If pull down transistor is on, then it will discharge the capacitance, and if pull up transistor will on, it will charge the capacitance. Now depending upon which transistor is on and which transistor is off, depending upon that, there will be time required to charge the capacitance or discharge the capacitance, and depending upon that, delay will be occurred. Okay, so consider, so for the purpose, so in case of when transistor inverter is on, we can say when applied voltage is high, the pull down transistor is on, so there is a only 10 kilo ohm resistance will be there, and when pull up transistor is on, there is a 40 kilo ohm resistance, that is 4:1 inverter. So delay will be different. Okay, so to get equal delay, so we have to consider a pair of cascaded inverters. So delay in this pair will be constant irrespective of the supplied voltage, irrespective of the sense logic level transition. That is, for if this transistor, if applied voltage is high, then pull down transistor will be on, and here pull up transistor will be on. Applied voltage is low, this pull up transistor will be on and pull down transistor will be on. Hence, so delay associated with this will be like this. When applied voltage is high, this pull down transistor is on, means there will be only 10 kilo ohm resistance will be there, and this is 1 square Cg. So as we discussed, it is a 1 2. And in case of pull up transistor, so there is a 40 kilo ohm resistance, and here it is a 1 square Cg capacitance. So therefore there will be the 4 2. So therefore time required for one pair, that is overall delay in nmos inverter pair, it is 1 2 plus 4 2, that is equal to 5 2. Okay, so time required, overall time delay in one pair, it is 1 2 plus 4 2, it is a 5 2. If suppose applied voltage is low, at that time this transistor, that is a pull up transistor, will be on, there will be 10 kilo ohm and 1 square Cg. So here you will get 4 2, and here this transistor will be on, pull down transistor will be on, and here you will get the 1 2. So therefore 4 2 plus 1 2, that will be 5 2. So for one pair, time delay is equal to 5 2. This is in case of nmos inverter. In general, for nmos inverter pair, time delay is equal to 1 plus Z pull up to pull down ratio, okay, into 2. Now let us suppose for this 4:1 inverter, 4 by 1, you will get the 4 plus 1, that is equal to 5 2, it is for 4:1 inverter. Likewise, suppose Z pull up to pull down ratio is 8:1, so 1 plus 8, that is equal to 9 2 will be the delay for 8:1 inverter pair. Okay, so in this way we can calculate inverter delay in case of nmos inverter. Okay, now we will go for the cmos inverter. Now cmos inverter, you know that the CMOS inverter, it will have one p-type transistor, that is pull up transistor, and one n-type transistor, that is pull down transistor. There are two transistors and gate of the two transistors are connected together, so therefore input gate capacitance is a double. Gate capacitance is a double. Here it is minimum feature size, here it is also minimum feature size, 1:1 transistor, here also 1:1 transistor, and for 1:1 transistor 1 square Cg, 1:1 transistor 1 square Cg. So total capacitance is a 2 square Cg at the input of the CMOS inverter. Okay, so this is 2 square Cg it is shown. So here it is also 2 square Cg it is shown. Now CMOS inverter natural asymmetry of equal size pull up and pull down transistor. What is meant by natural asymmetry for equal size of the pull up and pull down transistors? Means here, means in case of CMOS inverter, there is a p-type transistor and there is a n-type transistor. This is PMOS and this is nmos, and you know that the mobility of electrons and mobility of holes is less, that is a 2.5 times is less, and hence pull up transistor, that is nmos inverter, pull up transistor is a PMOS inverter, pull up transistor is a PMOS transistor, and this PMOS transistor it will have more resistance because of mobility of holes. Mobility of hole is less as that of mobility of electrons, and hence PMOS inverter, PMOS transistor, it will have more resistance, and already we have discussed it is, and the p-type transistor it will have 2.5 times as that of n-type transistor resistance. Okay, so therefore it is asymmetric transistor, or asymmetry will be there. So here you know that here for pull down transistor, for minimum feature size, that will be having on resistance, on state resistance it is a 10 kilo ohm, and for PMOS transistor on state resistance for minimum feature size it will be 25 kilo ohm. Okay, and hence here it is shown, you can see here, that is for pull down transistor the resistance it is a 10 kilo ohm, and here for pull up transistor resistance it is a 25 kilo ohm. Okay, now if we consider a CMOS inverter pair, so in case of first inverter, if we apply high going pulse, then pull down transistor will be on. So therefore this 10 kilo ohm is driving input capacitance of next, that is 2 square Cg. So 10 kilo ohm and 2 square Cg. So 2 kilo ohm is a minimum RS into 2 square Cg. Okay, so here it is a 2 tau, it is the time delay, and here pull up transistor will be on. So here it is, and this pull up transistor is charging this capacitance, that is input of the next, so that is 2 square Cg, and this it is a 2.5 times of 10 kilo ohm, that is 25 kilo ohm, and hence time required to charge this capacitance it is a 5 tau. So for this stage, for first stage it is a time delay is a 2 tau, and for second stage time delay is 5 tau. So for one pair it is 7 tau is the time delay. If reverse, that is if it is a low going pulse, pull down transistor is off but pull up transistor will be on. Now here 25 kilo ohm is charging this capacitance, so therefore it will have delay is equal to 5 tau, and here pull down transistor will be on, and pull down transistor is on, and hence so time required to charge this pull down this capacitance is equal to 2 to, that is through 10 kilo ohm. So therefore time required to discharge this capacitance, that is 2 to, and therefore time required is equal to 2 to. So total time 5 to plus 2 to, it is a 7 to. So for CMOS inverter, time required to time delay is equal to 7 to. So as we have seen, that is asymmetry of the resistance is eliminated by increasing the width of the p-type transistor. We have already discussed how to decrease the resistance. To decrease resistance, we have to increase the width. But so here asymmetry resistance is eliminated by increasing width of p-type device, that is p-type device channel, by a factor 2.5 times or 2 to 3 times. Okay, 2 to 3. But as we increase the width, you know that the gate capacitance increases by the same factor. Okay, and hence again delay is going to be increased. Okay, so you can go through the rise time estimation and fall time estimation, that is in detail you can see in the book, that is time required to rise or time required to charge the capacitance, that is rise time estimation, and time required to discharge. So in case of CMOS inverter, time required to charge means time required to rise. At that time p-type transistor will be on, that is pull-up transistor is on. Okay, and T rise is given, or the final answer for this is equal to 3 into CL, that is the charging capacitance, and BP divided by BP into VDD, where in first unit or in first module you have discussed, you know that is BP is a constant and it will depend upon the permeability of the layer, that is SiO2 layer, permeability of the free space, mobility of holes divided by thickness into length as to width ratio. So you know that this equation, and depending upon that equation you will get the final equation. It is equal to 3CL divided by BP into VDD. So rise time estimation you go through the detail. Okay, so there is a simple derivation for rise time estimation. Okay, likewise the derivation for the fall time estimation, that is 3CL divided by BN divided by into VDD. Okay, so time required to fall or time required to discharge the capacitance, that is the fall time estimation, that is tau f, it is equal to 3CL divided by Bn into VDD. Now if we take the ratio of rise time to fall time, it is tau r divided by tau f. So ultimately remaining terms will be get cancelled and it will be BP by Bn. Okay, it will be BP by Bn, and hence so again BP will be depend upon mu n, and mu n is equal to mobility of electrons and mu p is the mobility of holes, and mu n is equal to 2.5 times mu p. Hence Bn is equal to 2.5 times BP. Okay, for the same size transistor. So therefore ultimately you will get rise time is equal to 2.5 times fall time. Okay, fall time will be smaller and rise time will be larger. Okay, as in case of fall time n-type transistor is on, and in case of rise time p-type transistor will be on, hence ultimately rise time will be 2.5 times more than the fall time. Okay, and hence we can mention there will be we'll get conclusion, or we can write there will be one conclusion in case of rise time and fall time. The rise time and fall time is inversely proportional to the supply voltage. So here rise time and fall time is inversely proportional to the supply voltage. This is one conclusion. Another conclusion, rise time and fall time are proportional to the capacitance CL. Rise time and fall time is proportional to the capacitive load. It is proportional to the capacitive load, directly proportional. And rise time is equal to 2.5 times fall time for equal number of equal length as to width ratio of n type transistor and p type transistor. Okay, these are the conclusion. Okay, then next, driving large capacitive load. The large capacitive load. Okay, what is the large capacitive? A large capacitance load problem arises when a signal to be transmitted from on chip to off chip destination. Okay, when a large capacitive load problem arises when a signal to be transmitted from on chip to off chip destination. Off chip capacitance is generally higher than the on chip capacitance. Okay, and it is denoted by a CL, that is the large capacitance. Okay, and this large capacitance is of the order of 10 raised to 4 square Cg. Large capacitance is the of order of, it is larger than the 10 raised to 4 square Cg. Okay, a capacitance of this order will be driven through a low resistance, otherwise long delay will take. Okay, so we have to take care that whenever the capacitive load will be larger than the 10 raised to 4 square Cg, 10 raised to 4 square Cg, when the capacitance is larger than this size, then we have to drive with the smaller size resistance, okay. So that's all about today's video, and then we'll discuss about the how to decrease the delay, okay, in the next slides, okay, in the next video. Okay, so today we'll stop.